Hello, and welcome to Chapter 4, Section 4. Today we're talking about Part 2, the average value of a function and the second fundamental theorem of calculus. The first thing I want to talk about today is the average value of a function. So when we talk about an average value of a function, we're basically saying on an interval from a to b, whatever two numbers those are, the average y value is what we're looking for. And we can find this using integrals. So if we find the integral from a to b of whatever function that we're using, f of x dx, and then multiply it by 1 over b minus a, we're basically like dividing. You know how when you find an average, you divide by how many people or how many items there were? This is us dividing or multiplying by 1 over b minus a, that distance. So that's how we would find an average y value. So let's do a quick example. We're trying to find the average value of f of x equals 3x squared minus 2x on the interval from 1 to 4. So setting up using our average value formula, if 1 is a and b is 4, then plugging in we would end up with 1 over 4 minus 1, and then we'd find the integral from 1 to 4 of 3x squared minus 2x dx. Okay, so simplifying this out, 1 over 4 minus 1 is just 1/3. And then I'm going to multiply this by the integral, or the antiderivative of 3x squared minus 2x. So using the power rule, I would get 3 times x cubed over 3 for the x squared part, minus 2 times x squared over 2. And then we're looking for this from the endpoints of 1 to 4. So, simplifying this out even more, I end up with x cubed minus x squared from 1 to 4. So let me plug stuff in. So with plugging in the bigger number first, so the x equals 4. 4 cubed minus 4 squared, and then I'm subtracting that from 1 cubed minus 1 squared. So simplifying a bunch more, I end up with a final answer of 16. That means the average y value of our function f of x equals 3x squared minus 2x on the interval from 1 to 4 is 16. In other words, if you look at all the y values of this function between x values of 1 to 4, the average y value would be 16. Alright, the second part of this video is about the second fundamental theorem of calculus. So last video we talked about the first fundamental theorem of calculus, where we're just looking at integrals with endpoints, so definite integrals, and how to evaluate those. So now in the second fundamental theorem of calculus, we're still looking at an integral with endpoints, except this time one of those endpoints is actually a variable. So instead of like actual numbers, one of them would be an x. So it could be in the top one here or the bottom one, doesn't matter. But let's say we were given a function f of x. So notice here I put capital F because it's going to be the integral. So capital F of x equals the integral of some function. This time I'm using a different variable just to so that we don't mix up the x's over here, and then having x's in the function itself would just be too much. So I'm using t's now. So f of t dt, and then x is one of the variables inside the endpoints. If I'm trying to find the derivative of this integral, so think about it first of all, derivatives, integrals, they're opposite things, right? So if we're trying to find the derivative, so capital F prime of x would just equal my regular function with x's plugged in. So let me show you with actual equations here, because it's a lot easier than it looks. So let's say our capital F of x, our integral, is the function from 0 to x of the square root of t squared plus 1 dt. So here, notice that we're just using a different variable in the function itself, and it doesn't matter whether it's t or some other variable, but my x variable is in the endpoint itself. So we're asked to find the derivative of this. So what the second fundamental theorem of calculus says is take the original function, so the square root of t squared plus 1, and then just plug in x for it. So the derivative is just the square root of x squared plus 1. So the original function, plug in an x instead of using the t. That's it. That's it. Anytime you have an x as one of the endpoints, that's what you're doing to find that derivative. So let me do another similar example so that you can be reassured that this is just this easy. So this time we are looking at the integral from 4 to x, so instead of 0 to x, of the function t cubed minus 8 dt, and we're finding the derivative again. So the derivative, like we said before, if the function was t cubed minus 8, all I'm doing now is just using x instead of t. It'll just be x cubed minus 8. Okay, I know this is hard to believe. It's so easy, but here's why it works. So you know how we were saying a derivative and an integral, they're just opposites of each other. So really they're canceling each other out when we find the derivative of an integral. But you know how with integrals where we have these endpoints, we're still subtracting, when you find an integral with endpoints, you would have to do the antiderivative and then plug in your endpoints and then subtract them from each other. So here, what we're doing instead of finding that antiderivative, the integral part and then the derivative part cancels each other's out. But then we technically are still doing that subtracting. So all we're doing instead is if our function is t cubed minus 8, there's no antiderivative of it to find because of the derivative canceling out with the integral, but we still have to find those endpoints of x and 4. So when I plug in my top number into my function, it would end up being x cubed minus 8, and then we subtract it from the plugging in the 4 cubed minus 8, but then, this is the part that's if you think back to our derivatives, this was kind of like chain rule. Because whatever we plugged in, we were also supposed to be multiplying by the derivative of whatever. Because we are technically finding a derivative, we're looking for f prime of x. So when we find the derivative using these endpoints, we also needed to do chain rule to multiply by the derivative of whatever we were plugging in. So with the x, the derivative is just 1. When I multiply by 1, it doesn't do anything, it just stays the same. When I plug in the 4, the derivative of 4, since it's a constant, is just 0. So when I simplify this out, I end up with x cubed minus 8 times 1 is just x cubed minus 8, minus 4 cubed minus 8 is some number, but then when I multiply by 0, I'm just subtracting from 0. So in the end, I end up with x cubed minus 8. So obviously this is the long drawn out way of how to do this, but this is why it works. So really, if you can just remember, just plug in x instead of t, that'll give you the correct derivative. All right, for my next example, I want to do one that's slightly more complicated now. So as you can see here, my f of x, this time when I find my integral, my endpoints are pi over 2 and then x cubed. So what makes it more complicated here is the x cubed. But then my function itself is cos theta d theta. So we're looking for cosine, and again, like I said before, the variable itself, whether you use t or theta or any other letter, doesn't matter. Okay, but we're finding the derivative. So if we are trying to find the derivative of f of x, f prime of x is going to be, if this was just x right here, this cos theta, when we find the derivative of this integral, would cancel out, and so we end up with cosine, and instead of theta, it would just be x. But we have x cubed, so we're going to plug in x cubed instead of theta. But then that part about multiplying by the derivative of whatever that is, because we have an x cubed now, we also need to figure out the derivative of x cubed, which is 3x squared. And then when we subtract, because the pi over 2 is just a constant, the derivative of pi over 2 would just be 0 times the cosine of plugging in pi over 2. So really I'm just subtracting by 0. That part doesn't matter. So my final answer ends up being 3x squared times cosine of x cubed. So things just get a little bit more complicated when you have an endpoint that's not just x. So if you have x cubed or something else, then you also have to find the derivative of it. All right, this next example, I'm going to complicate it just a little bit more again. So this time, when you look at your integral, we're going from 2x to 4. So notice this time the x is on the bottom, so it's like the smaller endpoint, and we're still finding the derivative. So when this is the case, our second fundamental theorem of calculus only works if x is on top. But we have that one property of integrals where if your like numbers are switched, where like the smaller one is on top instead of on bottom or something like that, you can just rewrite it. So I would be able to rewrite this, so before I find the derivative, so this is just f of x equals, when I put that negative in front, this switches my endpoints. Okay, so now that x is in the right spot, now we can find the derivative. So f prime of x is going to be negative, and then our function, instead of t squared plus t, it'll just be us plugging in the 2x instead of t. So it'll be 2x squared plus 2x. And then because it's 2x and not just x, we'd also need to multiply by its derivative. So the derivative of 2x is 2. And then we would subtract that from plugging in the 4, but then the derivative of 4 is just 0. So we end up with subtracting by 0. So simplifying this out, we end up with negative 8x squared minus 4x. Because I move the 2 back to the front, so that it'd be negative 2 times 4x squared plus 2x, and then distributing. All right, couple more examples. So this time, again, slightly more complicated. Now we have x's in both the top and the bottom. So with this integral, we're still doing the same thing as before. We're finding the derivative, so the integral will get canceled out. But when we find the derivative of f of x, we're going to have to plug in both the x and then subtract out plugging in the negative x. So it'll end up being x cubed when I plug in x into the function of t cubed. The derivative of that is just 1, because the derivative of x is just 1. And then we're going to have to subtract me plugging in negative x instead of t, but then the derivative of that is negative 1. Okay. So I get to subtract and multiply and simplify this out. I end up with x cubed plus, because minus a negative 1 times negative x cubed ends up being 0. Cool. All right, this last example is actually at the request of one of my viewers from a previous video. Thanks for watching, by the way. So this one, we're looking for the integral from 3x to x cubed. So I put it last because it was probably the most complicated one, of the function t cubed plus 1 raised to the 10th power, and we're looking for the derivative again. So here we go. If we are looking for the derivative of f of x, then our function itself, remember, stays the same because we are finding the derivative of the integral, and that would cancel out. But then we got to plug in our endpoints. So instead of t, I'm plugging in x cubed. So that gets raised to the 3rd power plus 1, and all of that gets raised to the 10th power. Ooh, a lot of exponents in there. All right, and then we are subtracting, so this time I'm plugging in my 3x. Cubed plus 1 raised to the 10th. Okay, but because both of these endpoints are not just x, we also need to deal with their derivatives. So in the first one, the derivative of x cubed would be 3x squared. In the second one, the derivative of 3x would be 3. So all of that would need to get multiplied out. There's a lot of exponents in here, so I'm going to try to simplify this as best as I can. So I'm going to put that 3x squared first. X cubed cubed would be x to the 9th plus 1 raised to the 10th power. Minus, and I'll put that 3 in the front, 3x raised to the 3rd power would be 27x cubed plus 1 raised to the 10th. And at this point, there's not a whole lot we can really do to simplify this. I mean, there's a greatest common factor of 3 that I can factor out, but otherwise, that's kind of it. So maybe we'll factor out the 3. That leaves me with x squared times x to the 9th plus 1 raised to the 10th minus 27x cubed plus 1 raised to the 10th. And not that that's very much prettier, but it's more simplified than before. And that's it. That's it for this section. Thanks for watching. Don't forget to like and subscribe. See you next time. Bye.